Hello everyone, my name is Abdukhamıd MIRZAAKHMEDOV. Today I'm very happy to discuss about this project, machine learning project, which is transmission power allocation in non-orthogonal multiplexes in band-full duplex cellular systems. I worked on this project with Omer Waseem Al-Zaidi and Dr. Mohanad Alayedi at Haliç University in Istanbul, Turkey. Okay, our aim is too simple, which is to achieve real-time optimization by using convex programming and domain-specific feature engineering. And the main challenge in this area is non-orthogonal multiplexes and band-full duplex. So NOMA or non-orthogonal multiplexes that increases the system capacity by multiplexing the users in the power domain, but it requires successive interferences cancellation, which makes interferences management very important. On the other side, there is a band-full duplex, allows simultaneous transmission and reception on the same frequency, which doubles spectral efficiency but makes strong self-interferences. When these two technologies are combined, the interference becomes highly complex. In that case, we need to deal with the self-interferences, inter-user interferences, and dynamic channel variations. Most of the traditional resource allocation methods becomes too slow or too static for this environment, which creates the problem that our project tries to solve. But from our researchers, we found bunch of solutions for this problem. But why we need a new solution? Because existing machine learning approaches often rely on the deep learning or reinforcement learning models. While these methods achieve high accuracy, but they are computationally expensive and heavy, and lack of interpretability, which makes them unsuitable for real-time base station deployment. On the other hand, most of the classic optimization techniques like WMMCE or PSO can find near-optimal solution, but they are they take too much computation time, and sometimes it takes a minute for single iteration. It's extremely expensive. So here is a clear research gap. We need a solution that is accurate, fast, and explainable, and also practical to implement on a standard base station. Our proposal, as I said, is simple, which is a hybrid machine learning and optimization framework for predicting optimal user power allocation. Our goal is straightforward, that predict a power vector that satisfies quality of service requirements, minimize power consumption, and also reduce the interferences. To achieve this, we need to use two main components. First of all is feature engineering. In this step, we transform the raw channel data into the meaningful physical layer matrices, such as interference to signal, and channel stability, and signal to interference ratio. And the second step, which is convex optimization, we use these engineered features, which I mentioned above, to solve the constraint optimization problem efficiently. The key contribution here is showing that lightweight and interpretable model can reach near optimal performance when designed only with domain knowledge. Also, let's talk about system and dataset. So, we use non-orthogonal multiplexes in band-full duplex cellular setup with multiple users and subcarriers. The main focus is on interference management and power allocation at the user and transmission. To train our model, we generated a simulated dataset based on a realistic propagation environment. Also, I want to explain a little bit about our last project because it's really relevant to this project. So in the last project, we predict the interferences for the channel users. So in that project, we collected data from the 3 base stations and we did some feature engineering and we deploy our dataset to this project. So basically, the dataset which we're using right now for this project is made in the last project. So the dataset contains 7,500 data, which is collection from the 3 different base stations. And for optimal power values were generated using high complexity optimization techniques like CVXPY and PSO. This gives us a reliable reference point for training and evaluating the machine learning model. And before feeding the data to the model, we applied dimensionality reduction. Raw channel gains are often noisy and high-dimensional data, so we summarize them using statistical moments like an average, mean, standard deviation. Then we normalize all of the features to ensure consistent scaling during the training. This preprocessing pipeline makes training more stable and improves the model generalization. And this part is one of the important for our project. This slide highlights the most important part of our approach. We extract 3 key groups of features. First one is interference to signal ratio. In here we use this equation to extract interference to signal ratio from the dataset. This metric directly reflects interference's severity and is very important for understanding the signal to interference ratio behavior. Second feature is channel stability. We also use this equation, which is standard deviation of the channel gain over the average channel gain to get the stability. So this feature tells us how predictable the wireless link is across the time. The last feature is power station. The ratio between downlink and uplink powers, which are essential for understanding self-interference in non-orthogonal multiplexes power domain multiplexing. These features capture the physical behavior of the system much better than raw data, which is why they significantly improve the prediction performance. And there is a second part of our solution. Here we show the convex optimization problem we solve. The objective is to minimize the weight and sum of the total power in generated interferences. Okay, we use this equation, which includes the power consumption weight and generated interference weight. Based on this equation, we solve the optimization problem. And here we impose 2 constraints. First one is a quality of service constraint to ensure that signal to ratio constraint stays above the target threshold. Okay, the second constraint is the power limit that ensure we stay within the device transmission boundaries. Okay, so this formulation ensure that the predicted power values are not only accurate but also physically meaningful and safe to deploy. So we start talking about results. In these slides, we compare the throughput achieved by our method to the theoretical channel capacity limit. The results show that our method stays within 5% of the channel limit, and in operating region between 15 and 20 decimal signal to ratio constraint. You can see in the picture. This means we are achieving near optimal spectral efficiency while still being lightweight and interpretable. So next result is this slide reinforces the same observation we did above, that our machine learning optimized power allocation almost perfectly tracks the channel capacity curve, and that confirms the fundamental strength of our approach. So second result is bit error rate. In here, we analyze link quality based on the bit error rate and performance across the different modulation schemes such as BPSQ, QPSQ, and other modulations. Our optimized power points fall directly on the theoretical bit error rate curves, which shows that the model can maintain high reliability while selecting the best possible modulation order for maximizing the throughput. So also there is a key insight. The model achieves the optimal trade-off between reliability and spectral efficiency through the adaptive modulation, which is very good for our model. The next result is energy efficiency. In this experiment, we compare the original power allocation with our machine learning optimized power allocation. We observe an average 24.3% reduction in transmit power while still satisfying the signal to interference ratio constraints. This demonstrates that our method not only improves the performance but also contributes to energy efficient communication, which is very crucial for the future 5G and 6G networks. Also, there is our future importance for our model. The result shows that the domain error features dominate the prediction performance. For example, uplink bit error rate and uplink interference to signal ratio constraint contributes to more than 65% of our model predictive power. This strongly validates our hypothesis. When you incorporate physical layer knowledge into the future engineering process, even the lightweight machine learning model can approach the optimal performance. You can see in here of the key features, uplink bit error rate is 0.33%, uplink interference to signal rate is 0.31%. So, and I think this is the last slide, which is real-time deployment. Also, it is a conclusion part. So, one of the biggest advantages of our method is a real-time feasibility. Our model has extremely low computational cost and produces prediction in just a few milliseconds. This makes it ideal for deployment on the real base station hardware without requiring any expensive accelerators. We also compare our method to deep learning and classical optimization techniques and show that our hybrid model achieves the best balance between speed, accuracy, and hardware requirements. Also, for the future job, we are planning to use reinforcement learning model to solve this problem. So far, this is all work which we have done, and thank you for listening to our presentation, and we're happy to take the questions. Thank you.